Alright, so SVM is a very popular machine learning algorithm. I know there are a lot of videos out there about SVM, and chances are you probably have watched some of them before bumping into this one. But in a lot of those videos, equations are given without explaining how they come about. So for example, those equations describing the distance from points to the hyperplane and the margins, etc., they were given without explaining why that is the case. So in this video, I will start off from intuition and show how we can derive this algorithm step by step. So SVM tries to solve a problem called classification. In the classification problem, you are given a bunch of samples with labels, and you try to find the decision boundary to separate those labels, such that in the future, when you are given a new sample without label, you will be able to tell what's the label of that sample by looking at whether that sample belongs to this side or the other side of the decision boundary. So for example, you may have some data of the weight and the height of some dogs and cats. And if you are able to find the decision boundary to separate those data, in the future, when I give you a particular number of weight and a particular number of height, you will be able to tell me whether those numbers belong to a dog or a cat. And because those weight and height are the features describing the samples, those axes are also generally referred to as features. Now, as you may have realized, there can be a lot of decision boundaries, actually infinite number of them, separating those labels in this particular case. For example, it can be this one, it can be this one, it can be this one as well. All of the three decision boundaries separate the samples very well, but they are not equally good. So what SVM does is to find the best decision boundary among those based on its criteria. So let's try to plot the three decision boundaries separately and decide which one might be the best. I would argue the first one and the third one are not as good as the second one, because if you think about there's a new sample coming in, for example here, and we don't know what's the label it has, we don't know whether it's blue or red, we would probably think it is a red one because it is just closer to those red samples. But if this is the decision boundary, it would be classified as a blue sample because it is at the other side, the blue side of the decision boundary. So clearly this decision boundary seems to have misclassified this new sample. The same thing happens here. If the new sample is near the red samples, for example here or here, they would be classified as blue, but we would intuitively think they should probably be red. And hence the second one seems to be the best. Now, what is the problem? What went wrong here? If we look at the difference between the second decision boundary and the other two, we feel that the second one seems to have maximized the space between the decision boundary and the two sample groups. So this is our intuition, and actually that's the intuition of SVM. SVM states that the best boundary, the SVM states that the best boundary is the one that maximizes the distance between the nearest points to the decision boundary. Okay, so now we know intuitively where is the best decision boundary, but how do we find it? How do we find it mathematically and represent it mathematically? It turns out it's actually very simple. It's just representing a line and coordinates. So for example, if we have some sample that are red, we have some other sample that are blue, and those sample has the coordinates of x1 and x2, we can just represent this line L with beta naught plus beta 1 times x1 plus beta 2 times x2 equals 0. This form may not be familiar with you, but I bet you will be very familiar with this kind of form. When you have a y-axis and an x-axis, you know that any line can be represented by y equals kx plus b. You can just reshuffle x2 to one side and all the other terms to the other side to make this line into the form of y equals kx plus b. So if you are correct, this will be that form. And hopefully if you are comfortable with this form, you will be comfortable with this way of expressing a line. But essentially, they are just the same. If we have the line of this form, we can just re-express it using matrix. And if we let beta 1 and beta 2 to a vector of beta and x1, x2 as a vector of x, then this line of this whole thing can just be expressed into this way. You may think, why do we use beta to represent this beta 1 and beta 2 in vertical form and then do this transpose to make it like a horizontal form? Well, this is just a convention. We like to express all vectors in a vertical form, and when we need it, we just convert them into horizontal form by doing the transpose. Depending on the data you are given to begin with, you may have more than two features. So for example, in this case, if we think about red as cats and blue as dogs, in addition to maybe the weight and height of each cat and dog, you may also be given information such as the color of each cat and dog as the third feature. If that's the case, we can also express the decision boundary in a very similar way. And if that's the case, the decision boundary will no longer be a line, but a plane. And we can similarly express it in a vector form like this. And similarly, we can express that decision boundary in vector form, which has exactly the same form, if you look at it, of beta naught plus beta transpose x equals 0. The only difference is that the beta now have three variables because, well, we have three features. We have more than two variables now. And it turns out that it can be expanded to p number of features, and p can be just any numbers of a positive integer, for example, 1, 2, 3, 4, and so on and so forth. Even if we have p number of features, we'll still get the same form of decision boundary of beta naught plus beta transpose times x equals 0, and only beta and x needs to be kind of adjusted accordingly. And that's the reason why we want to kind of keep everything in the vector form, because it's just so succinct. It's just so convenient to express this whole thing in a single form, even if we have actually very different number of features. So now we know how to represent the decision boundary mathematically, and very interestingly, they are always in this very concise form. We are one step closer to finding the best decision boundary. If you still recall, the best decision boundary was the one that maximizes the distance between the nearest point at the two sides of the decision boundary, right? So then the question comes, how do we kind of find the distance between those points to this decision boundary? Let's have a quick review of the dot product, which will be very helpful in finding the distance between a point to a decision boundary. So the dot product between a vector A and vector B is simply defined as the product of the length of vector A and length of vector B, and also multiplied by the cosine of the angle between the two vectors. So if we draw a perpendicular line from the end of vector A to vector B, we can see that the length of vector A times cosine theta is actually just this length. I always think about this as shining a torchlight from this side towards B. So basically the length will be the shadow of A. So as you can see, if the length of B is 1, then the dot product will just be the length of A's projection on B, because this term becomes 1 now. And if the theta, the angle, is 90 degrees, that means the vector A is something like this, right? And then thinking about shining a light, there wouldn't be any shadow, or maybe just the shadow of dot here. So then the dot product is 0. Now, let's assume we have a decision boundary L here. As we have seen previously, this L can be expressed as beta naught plus beta transpose times x equal to 0. Let's assume there are 2 points, M and N, that are on L, and there is a vector B that is perpendicular to this line L, and this vector B intersects this line at x0. If we have a sample x, this x can be anywhere, let's just assume it's here. We want to find the distance between the sample to the decision boundary. It will be just this distance, right? Which is equal to this orange dashed line here. Because we know the point M and N are on this line, their coordinates should satisfy this equation. So if we plug them in, we should get these two equations. If we use the second equation to deduct the first equation, we get this expression. Notice that when we use the point n's coordinate to minus the point m's coordinate, we actually get a vector that is pointing from m to n. And because vector b is perpendicular to this line L, vector b should also be perpendicular to this vector from m to n. As we have seen just now from the previous slide, when two vectors are perpendicular to each other, their dot product should be equal to 0. So in this case, if we do the dot product between vector b and mn, the dot product should be equal to 0. If we look at these two expressions, we should realize that the vector beta transpose and vector b are both perpendicular to mn. So in other words, they can have the same direction. Actually, beta transpose may have the same direction as B or the exact opposite direction as B, right? So uh, what I'm saying is beta transpose can be either this way or this way. Either way, it will be perpendicular to this vector here, right? But it doesn't matter because we can always multiply by this expression with -1. It will still hold true. And if we do that, this beta transpose will just be opposite. In other words, we can always make beta transpose the same direction as B. If we divide them with their length, what we get is the unit vector in their direction, and they should be equal to each other. This unit vector here becomes particularly handy because, as we have shown on the previous slide, if the length of the vector b is equal to 1, then this orange dashed line here is just the dot product of vector a and vector b. So the distance from point x to the decision boundary is just this orange dashed line, which is just the unit vector of b's direction multiplied by this vector from x0 to x. And because of this equation, we can substitute b divided by the length of b with beta transpose divided by the length of beta transpose, and we get this expression. And there's another trick that we can play here. Because x0 is on this line L, so x0's coordinate should also satisfy this equation here. So beta naught plus beta transpose x0 should also equal to 0, which is shown here. And hence beta transpose x0 is equal to minus beta. We can substitute this with this term here, and we can get this expression. This is very interesting because it tells us that if we want to find the distance from a point to a line, we just need to substitute the coordinate of that x into that line's expression and then divide that with the beta transpose length. We now know the distance between any sample or any points to the line L or the decision boundary. And actually this is a major milestone because if we want to find the best decision boundary that maximizes the distance to the nearest point, all we need to do is to find out where is the nearest distance and how to maximize that distance, right? But before we go there, there's one more observation. That is the distance between those points, those samples, to the decision boundary is actually signed. So this observation comes from the dot product, actually. If you still recall, the dot product has a cosine theta in there. So if this angle between the vector b and vector x0 x is smaller than 90 degrees, this dot product is going to be larger than 0. In other words, if this sample happened to be in this region, it's going to have a blue label, and this theta here is going to be smaller than 90 degrees, right? And that dot product is going to be larger than 0. If that sample happened to be in this region, however, it will have a red label, and that angle is going to be larger than 90 degrees, and the dot product is going to be a negative number. Now, if we define a new variable y that is equal to 1 for all dots that has blue label and equals to -1 for all red dots, what do you think would be the sign of y multiplied by the distance? So from the truth table, you can see that for all the dots whose y is equal to 1, that is all the blue dots, their distance is a positive number. So if we multiply their y by their distance, it's going to be a positive number as well. And for all the dots whose y is equal to -1, that is all the red dots, their distance is also a negative number. So if we multiply their y by their distance, it will result in a positive number. On the contrary, if there's a dot which has red label, but at the blue side of the decision boundary, then its distance to the decision boundary is going to be a positive number, but its y is going to be -1. So its y multiplied by distance is going to be a negative number. The same thing happens to the other side of the decision boundary. So why are we doing this? Why do we define this new quantity of y multiplied by distance? Well, we define this new quantity simply because when we say that the best decision boundary is the one that maximizes the distance to the nearest points, we have made an assumption, an unstated assumption. That is, the best decision boundary will separate the blue labels and the red labels very well. In other words, all the blue dots should be at the one side of the decision boundary, and all the red dots should be at the other side. For example, in this plot, we as humans can see all the blue dots and the red dots and roughly guess that the best decision boundary will be one that's roughly here, right? It may be tilted somewhat, but it will roughly be here. It wouldn't be like this or like this. Because for those decision boundary, no matter how far they are to the nearest data points, they didn't even separate those points very well in the first place, right? But the computer doesn't know, right? The computer needs a quantity to tell it whether all the classification has been correct. So for example, in this case, as human, we may say, well, the best decision boundary should probably be somewhere here, right? It may be just this line. But if we don't define this quantity, y multiplied by distance, we just ask the computer to maximize the distance between the decision boundary and the nearest points, what computers see is this, and it may just find a decision boundary like this. And clearly that is not a decision boundary that we want. So with all the preparation, we can finally convert our intuition of SVM into a mathematical one. Our intuition about the SVM is that the best decision boundary is the one that maximizes the distance to its nearest points. This can be converted into three statements. So first of all, we pick a positive number m, where all the points' distance multiplied by their y is larger or equal to m. So in this plot, this m is simply the distance between the decision boundary to the nearest point, or the decision boundary to the dashed lines, right? And then we want to find an L that can maximize the m, basically just to maximize these two distances. Now, we know that L can be written in this way, and we also know that the distance of any point to the decision boundary can be written in this way. So here comes the textbook definition of SVM. Basically, we want to maximize the m, where y multiplied by the distance, which is this whole thing, is larger or equal to m for all samples. Notice that there's a constraint, that is basically as a vector, the length of beta is equal to 1. So if that's the case, then for the distance, this denominator will be equal to 1. So then the distance will just be the numerator, right? And hence this y multiplied by distance can just be y multiplied by the numerator. So here is a more tricky situation. In this example, we have some blue dots and some red dots, and it seems that there's an outlier of blue dot here. Intuitively, we would want to ignore that outlier while looking for the best decision boundary, and that would probably give us a decision boundary to something like this. But if we use SVM to find the best decision boundary, it's going to give us this one instead. The reason being that, as I've shown a few slides ago, all the dots that have been misclassified, that is, all the blue dots at the wrong side of the decision boundary, will have a negative y times distance. And obviously that is not allowed by SVM. So how do we fix this? It seems that what we need is some allowance for misclassification, right? What we need is to allow, to some extent, negative y times distance. So that is exactly what we're going to do. We're going to modify the SVM such that we are still going to look for the maximum m, maximum distance to the nearest point, but we will allow some samples to violate the rule. That is, for example, there's two blue dots. We will allow their y times distance to be negative. But the total violation should still be smaller or equal to some budget, because otherwise too many points may be misclassified than we are comfortable with. So this is, again, the textbook definition of this modified SVM, and this is often the SVM that is widely used. So basically, we still try to look for the best decision boundary that maximizes m, where y times the distance is larger or equal to m times 1 minus epsilon, and this epsilon is a larger or equal to 0 number for each sample. And for all samples, the total amount of epsilon should be smaller or equal to some budget, C here. So for these two blue dots, their epsilon1 and epsilon2 will be some number larger than 1, such that their y multiplied by their distance will be a negative number, right? So it's just larger or equal to some negative number. They still satisfy this condition. And for everyone else, their epsilon will be 0. So everyone else still has their y multiplied by distance larger or equal to m. They're still at the outside of the dashed lines. I'm not going to go through how to find this maximum because that's going to make this introduction less gentle. But instead, I'm going to show you the result. So beta is basically the sum of all points alpha times their y times their coordinates. So here is a new concept, that is the support vectors. So basically the support vectors are those dots that are determined to be the nearest to the best decision boundary. So basically those three that are actually on this dashed line. And for all points that are not support vectors, basically all the dots that are not on those dashed lines, those and those, their alphas are going to be 0. Right? And hence, this whole summation can be simplified into this summation. So we just need to look at all the support vectors, basically the three dots, because everyone else has alpha equal to 0. And we just need to look at whether they are blue or red. If they are blue, their y is equal to 1. If they are red, their y is going to be minus 1. And just sum their coordinate multiplied by this 2. Yeah, so basically alpha is not 0 for all the support vectors, and beta naught can be solved by substituting the coordinates of the support vectors into this equation and multiply by their y and let that equal to 1. So that will give you beta naught. And if you want to know what is the label for any point, you can just substitute that point's coordinates into this equation and look at the sign of the result. If we plug this beta back into this equation, we get this equation. If we want to know the label of any point x, we can just plug the coordinates of that x into this equation and find the inner product of that point with all the support vectors, right? And multiply by the support vectors alpha, which is 1, and what's their label, and plus beta naught. And we can determine that point x label by looking at the sign of the result fx. All right, so one last bit before I wrap up this introduction. So imagine this case where you have just two features for a bunch of samples, right? And then you try to use a line to separate those samples. And then clearly you can see no matter how hard you try, it's not possible to use a linear line to kind of separate those two samples. If only we can have a higher order decision boundary that can kind of turn here, and then we'll have a very good decision boundary, right? We can do that actually. We can artificially create higher order features. So for example, here I just square x2 to create a new feature. Let's just call it x3. So x3 is equal to x2 squared. And then I do almost exactly the same thing here. Notice that this line, even though it has higher order, is no longer linear. It can still be expressed in this way, provided that we just think that x2 squared is just x3, it's just a new feature, and we have a new coefficient beta 3 in front of x3. So basically, this is the idea. We no longer have this expression with x in it. Instead, the x has been modified by a function of h, right? So, for example, in the example just now, h1 is just a function that gives the same output as the input. x2 is the same, and x3 would be a function that gives a squared input, right? So this is basically h3 would just square whatever you input. X1 and h1 and h2 would just give the same x1 and x2 in this case. And it shouldn't surprise you that if we write the decision boundary in this form, we substitute the x with hx, the SVM will give us the same format of the decision boundary, except that the x now becomes h of x, right? And if you still recall, this angular brackets here is actually dot product of the hx and hx prime, which is a support vector. So it's the dot product that defines this new decision boundary. And hence, we can just define this dot product as the kernel function. Basically, it is the inner product of the features in transformed space. So what does this transformed space mean? So in this transformed space, we have feature of h1, x1, h2, x2, all the way to hp, xp, right? And in the transformed space, the decision boundary is still a linear function depending on all the features of hx, right? Although in the original space, the decision boundary is not linear at all, right? There's power of 2 here. One more thing that's very interesting is if we look at the decision boundary that is dependent on this dot product of h of x and h of x prime, and the h of x and h of x prime is dependent on x and x prime. So the decision boundary is actually dependent on x and x prime. And because of this, we don't have to care about what h is exactly, right? We can just define this whole thing as the kernel function and specify the form of the kernel function. And that will give us directly the result of fx. So here are some common example of the kernel function. So for example, if the kernel function of a point x and the support vector is just the x transpose times the support vector itself, there's no h of x at all. Nothing has been applied on them. So we just get the original decision boundary without any kernel function, right? But of course, we can also specify this kernel function in a more complicated way. So for example, in this case, we specify in this. So for example, in this case, we specify the kernel function into an exponential function, something like this. And then we can just substitute this kernel function back into this, and then we get the decision boundary into this form. So this is called a Gaussian kernel, and is actually very widely used. So with that, I would like to end this introduction. I hope you have been following along and all the derivation has given you a clearer picture of how this SVM works.